equation. Everything we've done so far, we've been dealing with equations that are defined explicitly. So, for example, we might have an equation that looks like this: y equals 2x plus 4. That is an equation that's defined explicitly. Sometimes function notation is used instead. So like f of x, it could even be something like this: f of x equals x squared plus 3 over x. So these are defined explicitly because they are solved for y. So something that's not defined explicitly might look like this. It might look like y minus 2x equals 4. This equation is the same equation as the one above it, but this is not defined explicitly. It's not solved for y. For one like this, you might have something like xy minus 3 equals x squared. These two equations are actually the same thing, but they look much different in the way that they're defined. So everything we've done so far has looked like the first two, and we've had different rules for doing different things with those. So what we've already technically been doing just a teeny bit of implicit differentiation and not really even knowing that we're doing it. Because if we had this here, if we were finding the derivative of y equals x to the third, whenever we take the derivative of y equals x to the third, we have been writing this like sometimes we do y prime, but other times we do dy over dx equals 6x. And so whenever we write this dy dx stuff here, this is the derivative. I don't know why my pen is just erasing things. Derivative of y with, anytime I make a dot on my I, it's going away. It's not dot my eyes. With respect to x. So when we took the derivative of that y, the derivative of y was 1, because if we were taking the derivative of, just like if it was an x, if we had y squared, it'd be 2y, right? So if we took the derivative of 1y, we would just get 1. And then we would put dy dx because that's the derivative of y with respect to x. Over here, we take the derivative of 3x squared, we get 6x. We have not been writing this, but if we wanted to, we could do this. Derivative of x with respect to x. But dx over dx is itself, right? Something over itself, so that would just be 1. So that's why we haven't been writing it, because it's just equal to 1. Whenever we take the derivative of something with a y, so what we'll be doing today, we'll be taking derivatives of things with x's and also with y's. And so this example here, we've got d over dx of 3y squared. So whenever you see this d over dx, this is derivative of whatever's in the brackets with respect to x. And so we're taking the derivative with respect to x. We could take the derivative with respect to y, but it didn't ask us to do that. Or we could take the derivative with respect to a totally different variable like t or z, and we will do that eventually, but it's going to be a while before we get to that. So when we take this derivative with respect to x, we're going to have to do something a little bit different here. So we'll take the derivative like we normally would. So 3y squared is just going to be 6y. But because we took the derivative of a different variable, so we did not take the derivative of x, but rather y, we have to put the derivative of y with respect to x next to it. So you got to put a dy dx with it. So whenever we take a derivative of an expression that has a y in it, and we're taking the derivative with respect to x, we've got to put dy dx with it. Okay, so all this seems like sort of weird stuff right now, like why would you need to use this? So we're going to go into looking at, well, actually, we'll do a couple that we can actually look at some graphs of here in a second. Let's just do a couple examples of just taking derivatives right now. So here's a couple examples for you. I'll let you copy those down. You won't need much room for the first one. You'll need a little extra for the second. So if we're taking the derivative with respect to x of x squared plus 3y, then we would take the derivative of x squared, which would be 2x, and we're taking the derivative of x with respect to x, so we don't have to put anything there. If we did, we'd be dx over dx, which would just be 1. Plus, we've got to take the derivative of 3y, and the derivative of 3y is 3. But this time we took the derivative of an expression that had a y with respect to x. So even though the y is gone, we still have to put dy dx here next to it. Now right now that still kind of looks crazy and doesn't make a lot of sense. We'll look at where it's going to be used here in just a minute, but this would be your answer. Okay. If we had the second one, for the second one, we're going to take the derivative here, but it's going to be a little bit tougher because just as for that one, what am I going to have to use to take the derivative of x squared times y to the third? Got to use product rule. So what I'll do here is it's got to be f, which is going to be my x squared, times the derivative of the second. So the derivative of y to the third would be 3y squared. But anytime I take the derivative of a y with respect to x, I have to put dy dx next to it. And then we'll have plus y to the third. I do not put a dy dx here because I did not take the derivative of that. I just am writing y to the third. And then I'm going to multiply by the derivative of the first term, which is just going to be 2x. There. So we had f times g prime, and then we have g times f prime, and whenever we took the derivative of that part with the y, we had to put the dy dx. So you would clean this up a little bit. So you'd probably write it as 3x squared y squared dy dx plus 2xy to the third. questions? Okay, so let's get to looking at what this actually looks like. So here is a crazy equation. Y to the third plus y squared minus 5y minus x squared equals negative 4. And so we've got this crazy equation, and if I had written directions here, which I didn't, but I'm going to tell you what they are, I would want you to find dy dx. Find the derivative of y with respect to x. Because the derivative of y with respect to x gives you the slope of the equation at whatever point you're looking at. So I would like for us to graph this real quick. So let's see. Let me over here. Okay. So if we, and the great thing about Desmos is it will graph this stuff. Your calculator will not. Yes. I will get you some here in just a second. Okay, so it graphs this really cool looking equation here. So you see, I love to graph implicitly defined functions on Desmos because it is pretty easy to do, and they always look really, or they usually look really cool. Like this. So you got this weird graph here, and it's gonna be different than just a normal derivative of a function that we've looked at before, because if we look at our derivative, like let's say we're looking at our derivative at, let's see, how do I do this? Well, let me just put x equals negative 2. So like at x equals negative 2, I've got 3 different points where I have x equals negative 2. This is not a function. So I would have 3 different derivatives at that point. I would have 3 different possible answers for the derivative at those points. But we can still find a derivative that will give us our answer there. It'll take a little bit more work than those. But for right now, I just want to find the equation that will give us the derivative. So implicit differentiation is going to follow the same steps all the time. So the first thing you're going to do is you're going to take the derivative of both sides of the equation with respect to x. And so this one's fairly simple here because it doesn't require any product rules or quotient rules or any of those things here. You're just going to take the derivative, so you'll have 3y squared, but I just took the derivative of something that had a y, so I've got to put a dy dx plus 2y, and then also I need a dy dx here, and minus 5, and right here, even though the y is gone, I still need a dy dx because I took the derivative of a y with respect to x. And then for the last one, I'll just have a minus 2x, and that equals, if I take the derivative of negative 4 on the other side, what's the derivative of negative 4? It is 0. The biggest mistake that I see students make, and I do this myself often, is leaving that as a negative 4, forgetting to take the derivative of that, or just somehow looking at it wrong and thinking the derivative is negative 4. So make sure you take the derivative of both sides there. Okay, questions on that first part? Okay, the next thing you want to do is you want to move all the dy dx terms to the left and all the other terms to the right. Technically, it could be either side, but I just like to have the dy dx's on the left. So in this case, it'll look like this. Okay, and the reason that we want all the dy dx terms on the left on one side is because the next thing we're going to do is factor out the dy dx. So if we factor out the dy dx, it'll look like this. And then the last thing we'll do is we'll solve for dy dx. How are we going to solve for dy dx? Okay, right. Divide both sides by that 3y squared plus 2y minus 5 because dy dx is multiplied by that. So you end up with dy over dx equals 2x over 3y squared plus 2y minus 5. Okay, and so you've got a derivative here. The difference in the derivative that we have here versus the derivatives we've seen so far is you've got to know an x and a y coordinate before you can find the slope here. So, like for example, if I'm looking at this graph, if I want to know the slope of the graph at -2, I'd have to choose which point I was going to use first because we've got 3 points. Like I could use -2, 0, that'd be the easiest, or I could use either one of these other two, and it'll give me the slope of the line at that point. A lot of times for implicit differentiation, your answer still has a y in it over there in that side, which is a little bit different. So that means you'll have to know the y for this. And so here, it's okay to have x's and y's in your answer. In fact, most of the time you will have x's and y's in your answer. Okay, questions? And there's not a whole lot of things in calculus where I can give you step 1, step 2, step 3, step 4 instructions like I've done here. But implicit differentiation is basically always going to work like this. The only thing you have to watch out for in implicit differentiation is problems where you have to use a product rule or a quotient rule or something like that whenever you are taking the derivative. Sometimes those trip students up. But otherwise, it is actually sort of a step 1, step 2, step 3 sort of situation. Typically, students do pretty well with these as long as they know how to do the product rule and quotient rule and those things whenever they come along. So, if we have this equation here, x squared plus y squared equals 36, what is that the graph of? Anybody remember what that's going to be the graph of? We looked at them some. It's going to be a circle. What's the radius of the circle going to be? 6. What's the center of the circle going to be? It's going to be the origin. It's going to be at 0, 0. So this is a circle that we have here. So to take the derivative of this, you're just going to take the derivative using those same steps that we did for the last problem. So you'll have 2x, don't need to put anything with it because it was an x, plus 2y dy dx. And so that will equal, and the derivative of 36 is 0. And then so for this one, you're going to move the 2x over to the other side, so you'll have 2y dy dx equals negative 2x. You'll divide, you don't have to factor on this one because there's nothing over there to factor. So you just divide by that 2y. The 2's can cancel, and your dy dx equals negative x over y. Okay, questions? Okay, so with center at the origin, that one's pretty straightforward. This next one is also a circle. Where is the center located for this circle? 4, 3, and what's the radius of this one? 10. So that doesn't really matter for this particular problem, but I'm just testing to see if you remember what that is. So this one's going to be a little bit trickier whenever we're taking the derivative, because when I have x minus 4 squared, what am I going to have to use to take that derivative? Chain rule for that. So we've got an outside function, which is the x squared, and we also have the inside function. It's not a terrible chain rule because you're just going to have 2 times x minus 4 will be to the first power, and then you'll multiply it by the derivative of x minus 4, which is just 1. And then we'll have to take the derivative of the y minus 3 squared. Also requires a chain rule. So you'll have 2 times y minus 3 to the first power times, now we've got to take the derivative of y minus 3. So the derivative of y would be 1, but it'd have to have a dy dx with it. And then the derivative of 100 is just 0. So here I've just got 2 times x minus 4 essentially. I'm just going to distribute that 2. So 2x minus 8 plus, right here, both of the 2 and the dy dx are both multiplied by the whole y minus 3 here. So you might want to think of it like this: 2 dy dx times y minus 3. So when you distribute, you've got to distribute the 2 and the dy dx. And you can do that part in your head if you would like, but you'll get 2y dy dx minus 6 dy dx. Okay, so once we've done this, everything without a dy dx needs to go to the right. So we'll subtract that 2x, add the 8. Subtract that 2x, add the 8. So, and is it all right with you guys if I do this? I know whatever's left over here has a dy dx, so I'm going to go ahead and factor it out. Dy dx times 2y minus 6 equals negative 2x plus 8. Everybody okay there? Then you just divide, so we'll have dy over dx will equal negative 2x plus 8 over 2y minus 6. Now, you're probably not going to see the answer left like this. You might know why that is. You can simplify it because everything there is divisible by 2, so you can think of it like you're factoring out a 2. So you'd have 2 times negative x plus 4 over 2 times y minus 6. 2's will cancel. or you could just divide everything by 2, either way. Yes, thank you. 3 there. So you'll end up with, I just like to write that as 4 minus x, just so the negative's not out there by itself out front. But you don't have to necessarily, over y minus 3. So that would give you your derivative at any point. Questions? Okay. All right, so these can also be used to find slopes of tangent lines. So you could, or full equations of tangent lines as well. So 6 is to find the slope of the line tangent to x squared plus 3y squared equals 10 at 1 square root of 3. And so slope of the line tangent to, whenever it says slope of the line tangent to, that's asking for dy dx. That's what we're looking for here is dy dx, and we have to find it at this point 1 square root of 3. So we got to plug that in whenever we find it. So we're going to find the derivative, so we'll have 2x plus, here we'll get 6y, but we must put a dy dx with it. And then derivative of 10 is just 0. So we will move our 2x over to the other side. So 6y dy dx equals negative 2x. We will divide both sides by 6y to get that dy dx by itself. And so dy dx will equal negative x over 3y. And so if I want the derivative at 1 square root of 3, then I'm just going to plug in 1 for my x and square root of 3 for my y. And whenever we do this, here's a little bit of notation for you here. So the notation you use, because we don't have like f of x notation, because typically like if we're plugging in 7, we'll do f of 7. But we don't have f of x notation that we can use here. So we'll have dy over dx, and then we'll put this line right here, which means such that, and we'll say x, y, equals 1 square root of 3, down here at the bottom of that line. And so in this case it will be negative 1 over 3 square root of 3. And I mean, you could rationalize the denominator or something here. There's a possibility they might. So if they did, then you'd get negative square root of 3 over 9 for that, because you have to multiply top and bottom by the square root of 3. You don't have to do that. So if it is that answer's there, or if it's free response, leave it negative 1 over 3 root 3. Okay, questions? All right. Here's just another one. And I'm actually going to change this just a little bit. I think I can change this. I'm going to change this to just at the point where x equals 3. But I'm going to write over here 3, 1, just in case this is a problem I really can't do that for. I think I can. Oh no, I might not be able to. I can. Never mind. Leave it 3, 1 at point 3, 1. Some you can. We'll do one as maybe a warm-up tomorrow where it doesn't give you the full, the x and the y coordinates, where you have to find the x or the y coordinate. But we can't do it with this one. Okay, so this is kind of a difficult one to take the derivative of, because you got where a lot of them have just been equal to a number. This one has variables on both sides, and not only does it have variables on both sides, but you can't just take a simple derivative on either side. So when we take the derivative of 3x squared plus y squared squared, we're going to have to use a chain rule. And when we take the derivative of 100xy, what are we going to have to use there? It's a product rule. It's kind of hard to see it sometimes because it's a very small product rule. But you've got an x and a y there, so you've got to use a product rule on that right-hand side. So chain rule over here, you've got the outside function is that 3 something squared, and then your inside function is x squared plus y squared. So when we take that derivative, we'll have 6 times x squared plus y squared to the first power times, and then you want to put parentheses around your derivative here. So the derivative of x squared is 2x, and the derivative of y squared is 2y, but we just took the derivative of something with a y, so we've got to put dy dx there with it. Questions there? And then on the right hand side, you've got to use a product rule here. So you'll have 100x times the derivative of y, which is dy dx, plus y times the derivative of 100x, which is just 100. Okay, so this is going to get worse before it gets better at first. On the right-hand side, nothing's too bad there. You just got a couple of things to clean up. On the left-hand side, we have 6 times a binomial times a binomial. So we're going to have to multiply these two binomials right here together. And to do that, you're going to have to distribute here. So it's going to end up being a little bit long. You'll have 6 times x squared times 2x is going to give us 2x to the third. X squared times 2y dy dx is going to be 2x squared y dy dx. Then we've got to do y squared times 2x, so we'll have plus 2xy squared. And then we'll have y squared times 2y dy dx, so we'll get 2y to the third dy dx. And that'll equal this stuff over here, 100x dy over dx plus 100y. And you could go ahead and distribute your 6 here, which is going to turn all your 2's to 12s. So 12x to the third plus 12x squared y dy dx plus 12xy squared plus 12y to the third dy dx equals 100 x dy dx plus 100 Alright, it's kind of a mess, but we've gotten down to the part where it's not going to be quite as difficult now, because now we need to move all our dy's, dx's to one side, all of our thank you, all of our parts without the dy dx to the right, and then we'll solve from there. So when I do this, I usually go ahead. You got all these have the dy dx. I go ahead and factor it. I know the dy dx will be out here. The 12x squared y does not change signs because it's on the left-hand side already. The 12y to the third does not change signs because it's on the left-hand side already. But this 100x is going to have to be a negative 100x because you're moving it to the left-hand side. And then this is going to equal, you'll have your 100y, and then you've got to move that 12x to the third over to the other side, so it'll become negative here. And you also have to move the 12xy squared. So it'll look like this. And so to get that dy dx, you're going to have dy over dx equals 100y minus 12x to the third minus 12xy squared over 12x squared y plus 12y to the third minus 100x. And you don't have to here, but it will probably make your life a little bit easier if you reduce that a little bit. So 112, you have 100s and 12s. What number could you divide both 100 and 12 by evenly? 4. So if you do that, it'll at least give you a little smaller numbers to deal with. So you'll have 25. Oh, I don't know what's doing here. 20. What doing? It's erasing half of my page. It's trying to make me lose my mind. 25y minus 3x to the third minus 3xy over 3x squared y plus 3y to the third minus 25. Turn into an eraser in the middle of writing. X. See there, it's turned to eraser again. Okay, so this is our derivative. But this one asks us for the slope of the tangent line at the point 3, 1. So you got to plug in 3, 1. So x equals 3 and y equals 1. So you're going to find dy dx, and our notation for this is we put this long line right here, and xy equals 3, 1. And then we're going to plug in. So we'll have 25 times 1 minus 3 times 3 to the third minus 3 times 3 times 1 over 3 times 3 squared times 1 plus 3 times 1 to the third minus 25 times 3. Alright, so you'll have 25 minus, let's see, 3 to the third is 20. 7. This is really 3 to the 4th because you got 3, and 3 to the 4th would be 3 times 3 times 3 times 3, which is 9 times 9. You'll get 81 there, minus 9 over 3 times 3 squared is 3 to the 3rd, so that's 27 plus 3 minus 75. Okay, so, alright, so together that's 25 minus 90. If we put those two together first, just because they add up to even numbers. And then here you'd have 30 minus 75. So this is going to give you negative 65 over negative 45. Both of those are divisible by 5, so if you divide them by 5, you'll get 13 over 9. So your slope at this point is 13 over 9. So it takes a while to get there, but eventually we have gotten there. This is one of the more difficult problems that you will see. I just want to look at this real quick, see what it looks like. I haven't graphed it. I just want to see if we can tell. So 3x to the second plus y to the second equals 100xy. So it gives you this really cool sideways infinity sign. So if we're looking at the point 31, if we do y equals, what do we just get? 13 over 9. 13 over 9x. Oh wait, 9x plus c. Slide it there. So let's see if we can get this to look right. Oh yeah, that looks pretty much like a tangent line should there. So we can say that this is probably not a perfect tangent line because the y-intercept may not be exactly at negative 3.4, but it's pretty close to what you'll have there. It definitely looks like it could be a tangent line. You're welcome, as you work on your homework, you're welcome to check your work with Desmos by just graphing it and then seeing if it makes sense that your slope is right. Because if we had got negative 7 for our slope of our tangent line, obviously that has a positive slope there, so it wouldn't be correct. Okay, questions? All right, let me see if that's all I had for you. I might have another one. I think it is, yes. Okay, so homework, which you'll have a good 40 minutes to work on it, so hopefully we can get a little ways on it. Homework is going to be on page 179. So do 1 through 19 odd, and then 41 and 43.